In this subsection, we're going to go a little bit further with our coverage of essential theory. So we're going to talk about some additional tools to add to your arsenal that will enable us to build deeper, even more efficient neural networks on larger data sets, larger, more complex data sets. To get started, let's recap where we are so far. So we have figured out how to do calculations within a neuron. We have some X that is input into the neuron, and then we learn weights that are optimized to those inputs. We have a bias in each neuron, and together the sum of these is Z. We pass Z through an activation function, which could be a sigmoid, a tanh, or a ReLU neuron. And then each of these neurons is represented by these neurons within our larger neural network diagram. So within this neural network, we have an input layer. So these could be like the images, the MNIST digits, or any kind of picture or input. Then we have hidden layers that are doing the computation, and those hidden layers pass to some output layer where we're comparing the output of the network against the true outputs that we're trying to output. With each layer of depth that we add into the network, we have increasing levels of abstraction that are possible. So for images, we'll typically see edges being learned in the first hidden layer, and then further layers are combining those to have more complex representations. In order to learn, we need to know how wrong we are. We do that with cost functions. So we used cost functions to figure out how far off we are from the true output that we're trying to have. And then we use gradient descent to minimize the wrongness of the cost function. And we can back propagate our gradient descent through the network so that we can learn with multiple layers of neurons. And we've also talked about a couple different kinds of layers that we can have. So mostly we've been using dense or fully connected networks where each of the neurons in one layer input to all of the neurons in the next layer, and so on. So these are dense or fully connected networks. And we've also talked about softmax layer, which is typically used just at the very end on the top layer of the network to output a probability, a class probability of what the network is guessing. So moving on to some new theory here. When we start with a fresh network, we know what our X's are, we know what our Y's are, but how do we decide on what our weights and our biases should be at each neuron? How do we start our W and our B? So as the network learns, it figures out what the optimal weights and biases should be. But when we start off, what kind of values should we initialize this network with? When we're deciding on what kinds of values we want to initialize the network with, we make those decisions ourselves as the person creating the neural network, as opposed to the weights and biases after the neural network has been doing some learning. So when we initialize those values, how do we choose them? Well, we probably don't want to have a very strong opinion as the person creating this neural network. We want the neural network to have relatively uninformative weights and biases. So we could have zeros as our weights and biases. But that actually turns out to be a bad idea, because if we have zeros at all of our weights and all of our biases throughout the network, then there's no kind of randomness in there for the neural network to discover what possibilities work better or not. So let's not use 0. We're going to do an experiment in lesson 4 to see the effect of trying to initialize a network with zeros. So how about values near 0? We could draw samples from a uniform distribution. So we could have values near 0. So we have some probability distribution, and we want to be picking values near 0. So we could limit ourselves to picking values from a distribution that's evenly distributed from -1 to 1. So we're going to say I want to have small weights that aren't too far away from 0, and we'll just pick some random values from this distribution, anywhere between -1 and 1, and we'll throw those in. That's one way of doing things. Another thing we could be doing is we could be using a normal distribution around 0. So then we're tending to pick values that are very close to 0, and we less frequently take values that are further away from 0. We could even decide to truncate it so that we're saying, well, I'll take a normal distribution, but nothing that's too high or nothing that's too low. We're only going to take values from this truncated normal distribution. We'll try those later on. But for now, we're going to say that those are not optimal. And we'll see some examples later as to why that is. Essentially, when we have those uniform or normal initializations in our weights, when we pass them through the activation function, they become highly non-normal. They move quite away from 0. So some clever gentleman, Xavier Glorot, who was at the University of Montreal at the time, but now at Google DeepMind in London, he came up with some clever initializations that give us values near 0 after they've passed through the activation function. We'll illustrate this in lesson 4 as well. For now, we can say that using a Xavier Glorot initialization is a really good idea. And in fact, we can do it 2 different ways. So we can use a Xavier Glorot uniform or normal initialization. The next thing I want to talk about is gradient descent. Now, we talked about gradient descent yesterday. Let's recall quickly. It's this idea that we can, when we want to minimize our cost in the whole network or at an individual neuron, we know with our random initialization, or however far we've progressed with our training so far, we know how much cost we have, and we want to make a step in the direction of lower cost by changing whatever parameter in the network we're trying to optimize. So this could be a weight or a bias. And there are a few more helpful things to understand about gradient descent here. So one thing is the learning rate. So recall that earlier, while we were going through a code demo, we increased our learning rate in our network from 0.01 to 0.1. So we increased the size of the step that we were willing to make with our gradient descent from, say, this very small step of 0.1 to a much larger step, 10 times larger, in fact. Now, in some instances, that's great. And in the network that we were training, that meant that we had validation accuracy above 90% in a single epoch as opposed to several epochs of training. That's great. But it's possible to increase this learning rate too much. So imagine if we, instead of increasing this 10 times, where we get closer to the minimum cost, we'd increased it 100 times. Then we'd overshoot by a huge margin. And in fact, and then when we try to get back to lower cost, we'd be overshooting again. We would just be taking steps way too large all over the place. Now that's a problem because we're never going to learn. Later on, we'll go through some examples where we learn too quickly, and that makes it difficult. So that's one thing that we want to take into consideration here. Another thing that we want to take into consideration is our batch size. So we have secretly been using mini batches this entire time. In all the networks that we've built, there's been a batch size parameter that I've set to 128. At the time, I told you to just bear with me. So now's the time to discover what I was doing with that 128. Essentially, when we have a large network, even the smallest ones we've been building so far have thousands of parameters. Later on in these live lessons, we'll be building networks with millions of parameters. If we try to, right here we only have one parameter, if we have millions of parameters that we're trying to do gradient descent on and to identify where the lower cost would be, with these large networks, millions of parameters, it takes a very long time, or it might even be computationally intractable to find the gradient with the full data set. So what we do is we break the data set into mini batches. This kind of technique is called stochastic gradient descent. Secretly, we've been using stochastic gradient this whole time. I just didn't want to introduce it too quickly. In stochastic gradient descent, we choose a subset of the full training data. So we've been choosing 128 samples from the 60,000 MNIST digits to train just mini batch at a time. There's pros and cons to this. So the smaller our sample size, the less representative it is of the whole data set. But the larger our sample size, the more difficult it may be to fit it into memory, or the longer it will take to do this gradient calculation. So there's kind of a sweet spot. 128 has been working fine for the MNIST digits. Later on, we'll figure out how to tune this hyperparameter to optimize it. The third thing that we're going to take into account is second order calculations. So what I mean here is that with gradient descent, to figure out where to make our step here, all we're taking into account is the slope of the line at this given point. A second order calculation is taking into account our momentum or our acceleration into the current time step. So we're considering how quickly the gradient has been moving in the previous step. There are a number of popular options in neural networks for choosing, for taking advantage of these second order calculations. One of those is ADA, GRAD. Another one is RMS prop. In these live lessons, we're going to focus on Atom. And the beauty of the way that Atom works is that this approach figures out how quickly we've been moving in the past, so that when there's an opportunity to make big steps in learning, so at the beginning of training, when we have these randomly initialized weights and biases, our network is very likely to have a high cost, and there's a lot of opportunity to be learning. So we want to be taking bigger steps. But then after we've taken a number of big steps in the beginning, we start to find our way towards the minimum cost, and here there's less opportunity to be learning, so we don't want to be making big steps anymore. We want to make smaller and smaller steps to eventually narrow down onto this minimum. So Atom uses momentum to make all of those calculations for you automatically. Alternatively, with standard stochastic gradient descent, you can set your network with a variable learning rate so that your learning rate slows down over time. You can set that manually. But once again, with Atom, all of this happens automatically. It's a beautiful thing. There's one big issue that is a bit of the elephant in the room related to gradient descent, and that's unstable gradients. So typically, this manifests as a vanishing gradient problem, where here I've drawn a little diagram with 4 hidden layers in a network. Over epochs, as we train, our learning rate decreases. At the very beginning, when we initialize the network with random weights and biases, there's a lot of learning to be done, and so learning progresses quickly. Over time, that slows down. However, the effect is more dramatic in deeper layers in the network. So the ones closest to the output y have the fastest learning rate, and then as we go deeper, the networks have orders of magnitude slower learning rates. So the deeper that our network becomes, the more difficult it becomes to train it. And that's because the layers closest to the output have lots of information about how they could be wrong, but as we get deeper and deeper, it becomes less clear how we should learn to be making these changes. We're further away from the right or wrong information at the output level. So this is a problem that becomes really big if we have dozens of layers, and we won't be getting into dozens of layers or hundreds of layers in the neural networks that we're building, but it's something to be aware of. In some situations, you can also have the opposite problem, though this is less common, where you have an exploding gradient, and in fact, the neurons further away are learning too quickly. Either way, the learning is out of control, and we have a very difficult time converging on what the optimal weights and biases should be. For our purposes, the initialization that we talked about already, as well as normalization that we'll get to next, should be plenty to help us mitigate the unstable gradient issues. With any kind of machine learning or any kind of model fitting in general, an issue that you can run into is overfitting. So let's talk about what that is quickly. So let's imagine we have some input x and some output y that we're trying to predict. We could have one parameter in our statistical model, and we could try to fit these lines as best as we can, and we might end up with something like a straight line like this. Now, that doesn't describe the data particularly well, so we might think, well, hey, I'm going to add in another parameter to my model, say x squared. And then in that case, we can fit these points better. Now that kind of thinking, in this situation, I think was the right decision. We should probably have two parameters in our model. But we could say, well, hey, I could fit these data even better if I had a dozen parameters. And then you can pretty much you can fit all of the dots exactly perfectly. But that last model, this pink model with all of these parameters, this model is not going to generalize very well on unseen data. So then when we try to predict some new data points, the overfit model won't give great results. Now, with our neural networks, we have thousands or millions of parameters, so overfitting starts to become a really big issue. It's something that we need to be sure that we're taking account of. Otherwise, our model will fit very well to our training data and very poorly on our test data. So there are a few different ways that we can mitigate this issue. We can add L1 or L2 regularizations to our layers. Now, this type of regularization we see throughout machine learning. Essentially, what we do with L1 or L2 regularization is we add a penalty for having large weights in our model. This tends to reduce excessive weights from being present and keeps only the most important ones around, the ones that are going to give us the best results on test data. A second approach, which is unique to deep learning specifically, is dropout. So this technique was invented by Jeff Hinton at the University of Toronto, and now Google as well. In this approach, it's intuitively so simple. We simply remove some of our neurons from the network. So with each step of training, we randomly take away, say, half of the neurons. So by getting rid of half of them, all of a sudden the network can't rely on any specific point in the network, and this tends to reduce overfitting as well. In fact, this type of technique is so effective that often it can be used on its own, and so we will be using dropout a lot in our networks going forward. The third thing that we can do is we can artificially expand our data. So with the MNIST digits, we have 60,000 training inputs. That gives us some relatively broad range of inputs that are possible that the network needs to get used to. But we could make all kinds of changes to those data before putting them into the model. So we could slightly rotate the digits, we could expand them slightly, we could move the digits within the frame, we could add noise to the images, and with other types of data this works as well. So if we were working with sound, we could add noise into the sound, we could rejig the timing of things slightly. So there are all of these clever ways that we can artificially expand our data set. Together or on their own, any of these three are great options. Up to this point, we've only had a couple of different layer types. I had layers in our arsenal down here, but we're going to start adding more layer types. So I moved them over here under initialization. I added the reduce fitting options that we had down here. So thus far, we've been making the most of our dense or fully connected layers in the hidden layers of our network, and we've been using softmax on the output to predict class probabilities at the end. Now we're going to add a few more types of layers into our arsenal. So the first one that we're going to talk about is a max pooling layer. So the way that a max pooling layer works is if we imagine that we had some image, let's say it has 8 pixels all the way across, so labeled 0 through 7 and 0 through 7 on this axis. What the max pooling layer does is it reduces the size of the image. So one very common way of doing this is to have a max pooling layer with a pool size of 2. So what it does is it looks at the 2 by 2 pixel box in the top left-hand corner of our image here, and it says of these 4 pixels, which of these has the highest value, which is the darkest, and then it takes just that one value. So let's say this value was the darkest one, and we assume that that is somewhat representative of this whole pool section, and then we move forward just having selected that one single pixel. Now we do that jumping some stride length. So typically you would pick a stride length of 2. So you look at then the next section of 2 by 2 pixels, and then 2 by 2 pixels, and 2 by 2 pixels. Then we move to the next row, 2 by 2, 2 by 2, 2 by 2, each time saying which is the darkest of these 4. We'll assume that that's somewhat representative of the 4, and we'll pool them all into one value. So then, in the end, this image that we had that was 8 pixels by 8 pixels ends up having only 4 by 4 pixels, and therefore only a quarter as many of the pixels that we started with. So we initially, this 8 by 8 image had 64 pixels, and by doing this max pooling with a pool size of 2 by 2 and a stride length of 2 by 2 as well, so 2 along the vertical as well as the horizontal axis. We reduced the size of our image from 64 to just 4 by 4, which is 16. So this becomes useful in making the complexity of our problems, of all of the weights and biases that we're trying to fit, a little bit simpler. The next kind of layer that we're going to be using is super easy to explain. It's really just an operation. So it's a flattening layer. And all that we're doing with this flattening operation is we're, say, taking a 2-dimensional or a 3-dimensional array and we're flattening it into probably a 1-dimensional array. So this is very simple to explain. We did these kinds of operations in our pre-processing with the MNIST digits. If you recall, we had 28 by 28 images and we flattened them into 784 by 1 arrays. So it's the same kind of idea. Typically, we'll use flattening to convert from a convolutional layer, which we'll cover next, into dense layers. So convolutional is the third kind of layer that we will be using in our networks in this lesson. We're adding into our networks in this lesson, and they require a bit more detail. So we're going to get building some networks with max pooling layers and flattening layers first, and then we'll come back to convolutional layers. There's one final technique that merits speaking about on its own here, and this is the idea of batch normalization. Batch normalization came about only a couple of years ago, but it is a recommended best practice today in building deep neural networks. Batch normalization ensures that the distribution of input data into each layer doesn't progressively shift layer by layer. So the advantages of including batch normalization are that, 1, we don't need to worry as much about our initialization parameters. 2, we reduce the likelihood of neurons saturating, so getting stuck at high or low output levels and not contributing much to the network and having difficulty learning. So we reduce the likelihood of neurons saturating, and therefore we learn optimal weights throughout the network more quickly. And the third benefit of batch normalization is that it has regularizing effects, so eliminating the need for dropout or other types of regularization in some instances. Without batch normalization, the shift in variables called covariate shift can become more severe the more layers there are in the network. So batch normalization is especially important at this juncture where we're about to start adding in more and more layers.